Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 17, a worksheet having to do with sampling distributions. So let's first save the QMD file in our working directory for the class. We'll open up that file and set the working directory to this location, the source file location, and render the file. Let's see. Okay, when that completes, then we'll open up the HTML file. All right. So this comes from a lab which has a shiny applet in it, which is why you've got this please wait. It like logs you into a system. It gives you a working session, and as you work through this assignment, you can change the bandwidth of the histogram, and it will create new histograms. You can do, I think there's a place where you can do sampling. Oh, maybe this is it. Sample size, you can go up to, say, 300 and see what that looks like, and so on. Okay, so anyway, we're going to not use the applet, but we're going to write the code that produces these plots, produces the samples, and also produces the plot. There is, however, some code in this assignment. In particular, it requires the tidyverse open intro and infer packages. The infer package is going to allow us to do resampling from a data set, but I'm going to show you that actually some of their code is not really sufficient to complete the job. But this is the assignment we're going to work with. So the basic premise of the data is from a recent Gallup report, where people are answering the question about whether or not people believe that the world feels science benefits them personally. Okay, I said that poorly, but does science benefit people personally or not? Okay, and there's a link to an article, and they find globally that 20% of people do not feel that the work scientists do benefits them, and that leaves, of course, the other 80% believing that scientists do benefit people. Okay, so what we're going to do is we're going to create a population, assumes a sample size of 100,000. That's pretty big. It's not global, but it's still big. And we're going to assign these percentages to, scientists doesn't benefit someone personally, and we'll assign 80,000 of that 100,000 to benefits. Okay, so here's our data then. We're creating a table which has only one column in it, and there's 80,000 benefit, and there's 20,000 doesn't benefit. And this gives us an imaginary population from which we can draw samples. Okay, we can plot this data. Okay, so if we in ggplot put in the data set, global monitor, and assign the x variable to scientist work. So this takes these two possible values, benefits and doesn't benefit. Geom bar creates a bar plot, and then we have some labels. We're actually blanking out the x and y axis labels and just putting a title. And we're flipping the axes. That means we're swapping x and y. So that originally scientists' work, this bar plot was on the x-axis and the frequencies were on the y-axis. But flipping it allows us to have a horizontal plot which has the benefit of the labels being horizontal and easier to read. Okay, so do you believe that the work scientists do benefit people like you personally, or yeah, benefits people like you. So I can tell I need to increase the size of this plot area. So we've got 20% at doesn't benefit and 80% at benefits. Okay. We also can count this up and calculate the proportions. Okay. We've seen this in a previous assignment, I think class 15. So we start with the data set. For this scientist work, we're going to create counts, which creates this column N. And we're going to pass, in fact, let's go to RStudio and start looking at this code. The other thing I'm doing here is I'm setting a seed, a random number seed, so that the random sampling is the same every time, but it only happens if you run it from the top to the bottom. If you rerun sections, you've incremented the random number generator counter, and so what happens after that may not be exactly the same. So anyway, we will, once you render this, you'll get the same results over and over again. Okay, so let's go ahead and read in our data, and we'll make our plot. And one thing that we noticed is we needed our plot to be wider. So these two lines, the figure width and height, let's copy that and bring it down to the top of this code chunk where we made the plot. We're going to put hash pipe, and those are the figure chunk options. And let's make the width equal to 8. And that should be wide enough now for the title. Okay, while that renders, let's look at this table that we're making. So we start with the data set, which has 100,000 rows and one column. And first we're going to do is count. Okay, so when we count, we get this table. Scientist work each level of science work becomes a row, and then we get a new column N, which is the frequency. We're going to pass this data set into this mutate function, and we're going to calculate N divided by the sum over N, and that's going to be our proportion. So we're going to add a new column P, which is that ratio. Okay, so that's how that works. Very good. Let's go back over here. I'm going to refresh the page because we increased the width, and now the plot totally fits. Okay, the unknown sampling distribution. So I have not taken all the text from here and brought it over to the assignment. I have brought all of the exercise text, but not the accompanying contextual text. Okay, I have though brought over the code that is relevant. Okay, so first we're going to describe the distribution of responses in this sample. Okay, how does it compare to the distribution of responses in the population? So first we need to draw a sample. So here is our samp1 is sample 1. The number of observations we're going to draw from the data set is 50. And so let's actually take a look at the help for this function so we understand how it works. So this is from the dplyr package. The function actually says that it's been superseded by another function called slice sample. This happens regularly with the tidyverse, where they had a function idea, it worked well, but then they thought about the problem differently later on, and they wrote a new function that hopefully does everything that the old function does, but in a better way, and maybe it adds some additional functionality. We're going to continue. So if a function has been superseded, it will still work. When it stops working is called deprecated. That is when it's not only been replaced, but the old function is not even supported anymore, and it may not even be available in the package anymore. Okay. Anyway, so let's not worry about the supersededness. Sample N will take a table and draw without replacement a number of observations. So we're going to sample from the data set 50 of these rows. So samp1 has 50 rows chosen at random from the original data set. Okay, there's the 50. Now, okay, so now the question is, describe the distribution of responses in the sample. How does it compare to the distribution of responses in the population? Okay. Okay, I'm trying to skip ahead. I probably shouldn't. Hint. Although sample n function takes a random sample of observations from the dataset, you can still infer to the variables in the dataset with the same names. So code you presented early for visualizing and summarizing the population data will still be useful for this sample. However, be careful not to label your proportion P, since you're now calculating a sample statistic, right? So P is the population proportion. We'll end up using P hat as the statistic that is estimating the population proportion. Okay, so now we've got some code here. I believe this code, I've either copied it from, okay, so I've sort of copied it from above. We've already made a plot like this, and we've already done some summaries. So I'm giving you some code to work with. So here's exercise 1. Let's calculate the summary. Okay, so samp1 is the data set. We're going to calculate a summary of that, and we're going to calculate p hat as being the estimated proportion from our data set. So let's run these lines. Here's our table. It's roughly 80% and roughly 20%. Okay, and you may have something different here. It depends on whether or not you seeded your random number generator, same as me, whether you've run this multiple times. Okay, but all right, let's plot our sample. And I've added a couple things here. In particular, p hat is what we want to plot, and I wanted p hat to be on the x-axis. So there is geom bar, which is what we used last time to create a bar plot, but there's also geom col, which creates columns like these bars, and the columns are actually the height that you specified in the y variable. Okay, so I'm specifying the y variable as p hat. That's the height of these bars. In fact, let me do this without the coordinate flip. We'll just do sort of one part at a time, just to refresh you about how ggplot works. So if I specify the data set and the axes, I get a plot with the x-axis and the y-axis. If I add to that a layer for the columns, there are my columns. The first one goes up to 78%, the other one goes up to 22%. This horizontal line that I'm adding a red dashed line at 20 and 80%, or 0.8, 0.2 proportions. And so those are giving me reference lines so that I can see how different what we observed in our sample is compared to the population. Then we've got some labels. The thing that I'm adding is the caption. So I'll run everything down to there. Red dashed lines are 0.2 and 0.8 reference to the population proportions. And then the coord flip flips the x and y axes. So now p hat's on the x-axis and scientist work is on the y-axis. Now these axes are still called x for the scientist and y for the p hat within ggplot, because that is the encoding that you did, but we are flipping the coordinates when we produce the plot. Okay. Anyway, so here you can then talk about how the observed proportions from your sample are pretty close to the true population proportions. So you can add some text there to answer the question. All right, exercise 2. Let's see if we go back now. I know that this will eventually time out because we're connected to this server that does this Shiny app. And if you don't use it for a long time, it will think that you're not there anymore and will shut off. So we may need to reload this page eventually. All right, would you expect the sample proportion to match the sample, Would you expect the sample proportion to match the sample proportion of another student's sample? Why or why not? Okay. If the answer is no, would you expect the proportion to be somewhat different or very different? Okay. So we're not working in teams right here, but the main idea is that if you run this again, right? So the short answer is yes, everyone's is going to be the same because I've put a random number seed here. So I've initialized the random number generator at the same point for everyone, so you'll all get the same sequence of random numbers. That will make them identical. Let's see what happens. Let's move this sample code down into exercise 1 so that all the code is together. So we'll generate our sample, then we'll calculate the summary, and then we'll make the plot. I'll delete this code chunk up here. Okay, so that way I can just click the run button, and let's watch our bars, see how they change. Okay, so from sample to sample, we'll get, oh, there's another exact, click. Oh, there's 3 in a row that were exact. Okay, there's a different one. So every time we draw a sample, you know, they're roughly similar, but they're different because of randomness. All right, let's end there because it just coincidentally got it identical. So you might just say here that, you know, assume that we didn't initialize the random number generator and observe that, you know, the differences you get from sample to sample and discuss what you get between samples. Okay. All right, exercise 3. Okay, good. We've got some code here. Take a second sample, also of size 50, and call it sample 2. So I don't think we've got code there to do that. All right, compare that with sample 1. Suppose you took 2 more samples of size 100 and size 1000. Which would you think would provide a more accurate estimate of the population proportion? Okay, so let's grab all this data or all this code up here because that might be handy. We'll paste it here, and we want to now, oops, wrong place. Exercise 3. We want to take a second sample and call it sample 2. So everywhere here where I'm going to do Control F to find and replace, I'm going to take sample 1 and replace it with sample 2, and I'm going to only look within the selection. Oh, if I click the selection goes away? Or I'm not sure. Okay, we'll do replace. Go on, replace. No more occurrences. I think my selection went away when I unchecked that. I was trying to illustrate that we want to just focus on the selection. Okay, now we've got darker. That way it doesn't accidentally replace sample 1 above with sample 2. Okay, so we'll replace, so find, next, there it is, sample 1 summary, so replace that, sample 2, 2, 2, okay. Now, that may have seemed tedious to go through find and replace instead of just doing it manually, but it has 2 benefits. 1, there's no typos, or it's the same typo every time, and then you can do another find and replace. The second part is that it finds every one, and sometimes it is hard for the human eye to find everyone. All right, so let's see what we've got. Exercise 3. Okay, anyway, there's a second example of this. What would we say about these 2 samples? So samp 1 and samp 2 are pretty similar. Okay, they're both random samples from the population. You're going to get proportions that are close to 0.2 and 0.8. Okay, suppose you took more other samples of size 100 and 1000. Which would you think would provide a more accurate estimate? So accuracy is about the number, our estimate, being close to the true value. All right, so we've seen how close these get. Let's just try putting in 1000 because that's the extreme case, and we'll click run. Let's see. So that's pretty close. Click run again. That's pretty close. Watch the variability as we go from sample to sample. These are not varying very much around this red line. Okay, it's only different by little bits. If we go back to 50 and repeat this, watch how much variability there is now. Okay, so you sort of get the idea that not only is each time that we run it closer when we had a sample size of 1,000, but it's also less variable between samples, right? Okay, so you can say something like that. Exercise 4. Let's go take a look. We've got some code here that calculates proportions, and and the main thing is it takes many resamples. So we're going to take samples of size 50, and we're going to do that 1,500 times. And for each of those 1,500 samples of 50, we're going to count up the proportions of doesn't benefit and benefit. We're going to calculate those proportions, and then we're going to filter out just the proportions for doesn't benefit. Okay, that's the estimate of something close to 0.2. We're going to add some code here because this does not always work, and so we're going to reinforce the code basically. All right, the question is how many elements are there in the sample? Describe the sampling distribution and be sure to specifically note its center. Make sure to include a plot of the distribution in your answer. Okay, so we can do that. Let's just run the code and see what we get. Here we've got a center of about 0.2, and it's roughly symmetric. This is pretty good. Even though the proportion is somewhat close to 0, this is quite symmetric because 50 is pretty large. There's actually a tiny bit of right skewness here. This right tail is slightly longer than the left tail because it has to be. The left tail is bounded by 0, so it can't go very far, so it has to be a little bit shorter. Whereas the right tail, the proportions can go all the way to 1. So you've got a lot more room. It will be a bit more right skewed. If we, just to show you a couple things, if we make this sample size 10, and we'll still do 15,000 repetitions, which is a bit extreme, but now we've got, it's really right skewed. We don't have a lot of information to estimate this proportion. Not only that, the right tail goes all the way up to 0.7. Okay, if we have a sample size of 1,000, it will take a bit longer to do that, and the bin width is a little bit too wide here. But here's 0.2, and the range is very narrow, from 0.15 to 0.25. So it's only 5%, plus or minus. It's 0.2 plus or minus 5% at most. So this is in fact, if we make the bin width a little bit narrower for each of the bins, we'll take a look at the same sample. There we go. This is looking more and more symmetric. This is the result of the central limit theorem, that the statistic, as the sample size increases, the sample mean approaches a normal distribution. And this is looking more and more like a normal distribution. Okay, what were we doing? All right, let's look at what this data set is. In fact, I want to walk you through this code a little bit so we know what's happening. So we start with our big data set of 100,000 observations. Then we do this repeated sample. I'm going to reduce some things here. I'm going to only do 10 reps of size. How about 10 reps of size 5? Okay, that might give us make it small enough that we can see what's happening. And this is happening with replacement. We actually don't need to do it with replacement. We could do without, because our population is so big. But here's the beginning of our data set, or the result. Notice that the data is grouped by replicate. Okay, so any calculations we perform will be done by this new column called replicate. The first 5 rows are all from replicate number 1, and we have 1 doesn't benefit and 4 benefits in that first replicate. In the second replicate, which are the next 5 rows, we have 2 doesn't benefit, and so on, up to the 10 replicates. From there, we're going to count, and we're going to count within the groups. So within each replicate, it's going to do the counting. Let's run that. Okay, so within each replicate, here's replicate 1, these first 2 rows, replicate 1, we have taken all the unique factor levels for scientific work, benefits and doesn't benefit. We've counted up how many there were. Okay, so we've got 3 benefits and 2 doesn't benefit. In the second replicate, we had 4 benefits and 1 doesn't benefit, and so on. Now, these numbers are different than what we saw before because when I reran this code, it drew a new sample. Okay, so as we run this code over and over again, we're going to get different numbers. We just need to sort of live with that. I could have saved the result and incremented, but I think I just want to show you the gist of what's happening. Okay, from there we're going to calculate p hat, these proportions. So given for each replicate, it's going to calculate p hat. Now here's where the code breaks. Okay, notice in replicate 3 we saw benefits and we saw doesn't benefit, and so there were 4 benefits, 1 doesn't benefit, so it was 80% benefit, 20% doesn't benefit, okay, of those 5 observations. So great. Doesn't benefit had 20%. What was the proportion for doesn't benefit for rep 1? Well, p hat for benefits was 1, so doesn't benefit must have been 0. But because the table did not have any observations with doesn't benefit, we don't get a summary there. So this is where the code doesn't work. What we actually want is we want to make sure that there are some zeros for doesn't benefit, because the next step is to filter, take only the rows with doesn't benefit, and we're going to then plot those proportions for doesn't benefit. However, we should have some zeros here, and we don't. Okay, so this is part of the technical part of doing this type of statistical coding. So this is where we can fix this. I'm thinking about this for a second. Okay, so let's go back to our counts after we've drawn our sample. So here we've got replicate 1, which didn't have any doesn't benefit. So there is a function called complete. It's in the tidyr package, which I think is automatically loaded with the tidyverse. So we can do complete. And what complete does is it completes the observations. For if you got combinations of factor variables, like replicate is a factor variable, which takes these integers, 1 of these for each replicate. You can think of it as numeric, but each of these replicates is sort of a category. It's not like 4 is more than 3. It's just another label. Okay, and it's convenient to label these numeric with numbers. Okay, and then so we've got that as one of the categories, and we have scientific work, which takes 2 levels, benefits and doesn't benefit. So what we want to do is we want to complete the data set so that anytime there's no benefit for a replicate, we get a new column, or excuse me, a new row that has the doesn't benefit with a 0 over at n. Okay, so let's look at the help for complete. We pass the data. That's what the pipe does. It passes the data in. Then we specify. Let's make some room here. Then we specify the columns that we're going to that we want. So let's see. So we've got complete. So we've got replicate, and we've got scientist work. Okay, let's just run that much and see what we get. Let's see. That's not good. I think, okay, error and reframe. I know why. This data set is grouped. So before we complete the, we have to ungroup. Okay. All right, so let's run that part. All right, so here's a case. Replicate 4, okay, had benefits were 5, and it previously didn't have a row for doesn't benefit, and now it's got NAs. But we actually want to fill that not with NAs, but with a value. So anytime you have to add a row, make sure that we fill N with 0. Okay, so let's run this part. All right, so here's an example, replicate 3, this case, where there were 5 benefits and 0 doesn't benefit. So now we've got all the zeros appear. Okay, so now their code is going to work. We can do something here. We have two choices. We can divide by the number of observations that we sampled, the sample size here, or we can regroup our data set. Probably let's do group by. Group by, and we're going to group by replicate. So we'll reform our replicate groups, then we can mutate, and then we can filter. Probably should ungroup again, but it doesn't really matter. Okay, then we can just keep the rows of the doesn't benefit. All right, so let's run this whole thing. Okay, we only have the rows for doesn't benefit. We've got the 0 rows that we used, that we got from the complete function. We've got their proportions over here. And now we can summarize the p-hats, and we've got our full sampling distribution. So finally, let's go ahead and increase this back up to 50. I don't know, 10,000 is plenty. Don't need 15,000. Okay, and run this. Very good. So there is our sampling distribution. I guess we want 15,000. Someone put it in the subtitle right here. Okay, right there. Okay, very nice. So let's run this one more time and then get the answers to the questions. How many elements are there in sample props? Well, if we look at the dimension, we've got 1,500 rows. I guess 1,500 is the number of elements. Describe the sampling distribution. Well, it is roughly symmetric, maybe slightly right skewed, but basically symmetric. And it's centered. Note its center. Its center is about 0.2, which is the true population proportion. Okay. Very nice. So those are things to write there. All right. You doing okay so far? I'm going to stretch. Sorry, this is going to be a long one, but I hope that you're learning through this example, right? One of the main things here is that even though the main thing to learn is that when you see a piece of code that looks like this was not just written like a sentence from the top to the bottom. It takes time to figure out what to do, add a step of complexity one at a time along the way until you actually get the result that you want. Okay. What else is going on here? We got a histogram. Okay. Yeah. You know what? We've got tons of observations here. What if the bin width was a little narrower? Interesting. Now, why does this happen? This happens because when you've got 50 observations, the proportions, what are the possible values of the proportions? Okay, so sample proportion 50, p-hat, let's look at the unique values and let's sort them. Okay. Okay. Oh, why don't I have zeros here? I should definitely, well, maybe I don't have any zeros. With a sample size 50, it might be hard to get exactly 0. So that's probably why. I don't see a 0 over here. Okay. Anyway, I'm just always concerned about my boundary points, especially because we just had this issue about zeros, but we definitely fixed that. Okay. So what do you notice here? That the proportions that you can get if you divide an integer by 50 is in increments of 0.02. So if you have a bin width of 0.01, your bins are too narrow, and you've got a bin that contains all the values, and then you've got a bin that's empty. Okay, so a bin width of 0.2 is the nice value to have here. It's just right. In fact, anything larger, and you would lose resolution. This is now too chunky, right? You've got a resolution of 0.2. Might as well plot it at 0.02. Okay. All right, exercise 5. Let's go over. So here's the timeout. We're disconnected to the server. From the server, we'll reload that. All right. Exercise 5. To make sure that you understand, okay, we'll go back here. Okay, so here it's talking about sampling distributions. We just generated a sampling distribution in the previous code of the proportion for doesn't benefit. Okay, and that's pretty much what this is talking about. Okay. All right, very good. Okay, exercise 5. To make sure you understand how sampling distributions are built and exactly what the rep sample n function does, try modifying the code. We've actually done this already when we were troubleshooting the issue. We changed 50 to 5. We are not there. We changed the 50 to 5. We changed the reps to, or no, we did reps to 10, something like that. So they're saying to sort of play along with that. And in this case, we want to do a sampling distribution of 25 sample proportions, and the size of each sample is going to be 10. We're going to put that into a new data set called sample props small. Okay? And then answer these 2 questions. That's easy. We'll just take all the code that we just wrote and copy that down to exercise 5. And instead of sample props 50, this is going to be sample props small. Okay, so here's a place where I would probably usually do a find and replace. I think it's just those 2 places though. Oh, here's a third one. Okay, and then what do we want? We've got 25 reps of size 10. 25 reps of size 10. Boom, boom, boom. Okay. Ugh. Yeah, so those sample sizes are pretty small, and we don't have very many of them. If you run this several times, you'll see how much it changes. Okay, it's sort of dramatic how if you were to see any one of these, you would start interpreting it possibly with a fairly strong conviction about what the sampling distribution looks like. But as you see through repetition here, that some of them are very peaky in the middle, some of them look a bit right skewed. This one looks even more right skewed with a peak at this one's like almost perfectly right skewed with a peak at 0.1, right? Whereas the true value is 0.2. That should sort of be the peak at 0.2. Look at this. It's sort of symmetric and sort of equally likely across 0.1 all the way to 0.4, putting 0.25 as the middle value, right? So it very, wow, look at that. It goes all the way up to 0.7. So it's very, very different. So when you've got small samples or very few repetitions, of course, the nice thing about repetitions is that you can increase that, only dependent on your computing power. But when you get small numbers for either of these, don't interpret the resulting sampling distribution very strongly. because you don't really have that much information. All right, what would we say here? Anyway, you know how many observations there are. It's the number of rows, 25. That's how many reps we have. And what does each observation represent? Okay, well, we can plot, or we can print out this data set. Each row is the proportion of doesn't benefit in one of the replicates. Okay. The only thing I will improve here, since we're dividing by 10, the bin width of about 0.1 should be about right. There is a tricky part of that about like where do zeros go. Oh, but these are centered at those individual points. So I think 0.1 is the better bin width for this histogram based on the possible resolution of our data values. Okay, so I think we've handled that one. All right, sample size and the sampling distribution. I don't know what this is doing here. It does make that plot though. Okay. Exercise 6. Use the app below. Okay, so we're not going to do that. We're going to write our code instead. To create sampling distributions of proportions of doesn't benefit from samples of size 10, 50, and 100. Use 5,000 replications or simulations for each one. All right, and then we're gonna plot all those. So I'm going to show you something that's very useful if you are doing a lot of statistical programming, and that is we're going to take the code. Where should we do this? This code is just fine. Okay, so let's start with the last piece of code that we ran, because that does generate the sample distribution for one case. All right. Let's maximize this. All right, so we're going to do sample props. This is exercise 6, I think. Okay, exercise 6. So I'm just going to call it exercise 6. We're going to take certain sample sizes. The reps are going to be 5,000 each. Okay, and it's going to go through and do the calculation. It can make a plot. Okay. So I'm going to do this a very nice way. This sample props I'm going to make into a list. What's a list? So actually, let me do this. Here's AAA is a list. Okay, there's AAA. It doesn't have anything. It's just like an empty bucket or an empty folder. And in that folder, you can put other things. So we can create an object called A, and that is, say, the number 1. Okay, so now AAA now has a list element called A that has the number 1. We can make an element B, and maybe this is the numbers 1 to 10. Okay, and so now AAA has a list inside of it with 1, and then B has the list 1 to 10. Not only that, but we can have lists of lists. So AAA $, how about X is also going to be a list. Okay, so now X is also a list in AAA, and X under X we can have X1, and that's maybe the letters, the first 5 letters. Okay, so let's look at AAA. So now we've got the A object, the B object, and then under X we have X1, and it's the first 5 letters. So you can nest all of these lists, and you can create this hierarchy. I do this all the time when I'm doing complex analysis, and I've got a bunch of similar analyses, and I want to package them in this object, and then I can traverse this complicated list structure and pull out the values that I need for my analysis to make tables and plots and so on. Okay, so let's get rid of AAA. Okay, RM is remove. All right, so I'm going to make a list called sample props example 6. It's empty right now, and I'm going to put some things in there. So we've got a for loop because we've got 3 sizes that we're going to do. We've got size 10, 50, and 100. So we're going to do from size is in the values of 10, 50, and 100. Okay, that's the beginning of our for loop, the curly brace, and we've got the end of our for loop down there. And everything inside the for loop we're going to indent. Next, we need iSize. iSize is going to take these values, 10, 50, and 100. Okay, so that is the size that we want. All right. So now each time it runs through here, it's going to take a sample of that size and do all the summaries. Okay. Next, we want to store each result in its own part of the list. And this is a little trickier because if you put specific numbers in here, like iSize takes the numbers 10, 50, 100, and so you'll get this list that has elements 1 through 9 are empty, and then element 10 has a result in it. And then you'll have 11 through 49 is empty, and then element 50 will have it. But we can label this if we change the number to a character. Okay, so I think I just want to run this and show you what the result is. I think this should all work. You know, I don't know. I make mistakes all the time. Maybe it doesn't. So sample, sample props, example 6. Okay. Okay, perfect. So we've got sample props. We've got these named lists. The first one is 10 because that's what iSize was, and it turned it into a character. And so this is the first 5,000 where the sample size was 10, and here are the proportions. Okay, and there's 5,000 rows of that. Then the next list object is 50. Is called 50, and now you can see the p-hats are in increments of 0.02 because it's dividing by 50. And then we've got of 100, and now you've got p-hats that are in increments of 0.01 because you're dividing by 100. Okay, so now we've got these three lists together. Well, yeah, technically in R everything is a list. But you've got three tables in this list. So now this is where things get cool. Let's see. Oh, you know what? We need one other additional part. We need some way of indicating that this table is from size 10 and that this table is size 50 and so on. So we've got this mutate statement here where we're creating some objects. So in there, let's expand this out a little bit. Give ourselves a little more room to think. Okay, so let's do size equals iSize. I think that should do it. Okay, let's run that and see what we get. I'm going to rerun the top one too because it's going to reinitialize the list. So we're not like overwriting the old list, but we're creating a new one. Okay, so now we have a size column, 10s, 50s, perfect. Okay, here's where things get great because we planned ahead. There's a function called bind rows. So let's look at the help for that. It's in the dplyr package, and it takes the rows from data frames, or it takes multiple data frames and binds them by row. That means if you're going to bind, it's like gluing, right? So if you bind by row, you've got a set of rows, and then you've got the set of next rows. From the next data set, from the third data set, you've got the next rows, and you're going to bind all of those together from top to bottom. If all the columns line up, in fact, it's going to figure out what the column names are, and it's going to align the columns appropriately. In this case, they're all identical, so it's going to line up perfectly. But let's just overwrite our original list, and we're going to update that by binding the rows from all of the individual lists. All right, so let's take a look at what that looks like now. Now we have a single table that has 15,000 rows, 5,000 for each of the three, and it's got sample size 10, 5,000 times, and then it's got the next one. Now all the data is in a single table. This is great because now we can make 3 separate plots in different facets. All right, so we'll start with our data set and our original plot code. Let's just plot this and see what we get. It's not what we want, but it does make a plot. Okay, a couple things here. We've got sample sizes of size 10, 50, and 100, and then the number of samples for each is 5,000. Okay, so at least we fixed the labeling. Then facets. I use facets all the time. Let's do a facet wrap where we're going to make separate plot areas for each size. And let's just do that and see what it looks like, and then we'll improve it. Ooh, I didn't like it. Facet wrap. Oh, I think for ggplot you need to do pluses. Okay. Okay, so there are 3 plots. Now, it makes it hard to compare if it's horizontal because we really want to compare along the x-axis. So let's make the number of columns equal to 1. Okay, so let's look up the help for facet wrap so you can see what I see. But now look at the x-axis, right? We go from 0 to 0.75, and now you can see what's happening in terms of the width of here. All right, so you've got the facet formula, which sort of specifies how you're going to, by categorical variable, how you're going to break up the whole plot area, number of rows, number of columns. Sometimes you want to free scales. In this case, we probably do. The y-axis here sort of is different for each of these. Notice that the top one's really short. So let's actually do a scales equals free y, and that will give each y-axis a separate minimum and maximum for the limits of the axis. The other thing is our bin width. Let's make that a bit narrower. Okay, so we've got this the spaced out one. That looks a bit better. Let's try if it was 0.01, maybe too narrow because this one will be separated too. I don't know. I sort of like that. Gives us a nice way. So now we've got a nice way of comparing. Notice that the facets are labeled 10, 50, and 100 at the top. Okay, so now we've got a beautiful way of comparing these 3 distributions. The only thing else I might add to this is the reference lines that we had before. So up here we had these horizontal lines for our bar plot. Let's bring that down. Now this isn't going to quite work because we're not drawing horizontal lines. We want to draw vertical lines. So geom V line is a vertical line. We don't have a y-intercept, we have an x-intercept. And we're only looking at the doesn't benefit, which is the proportion of 0.2. So let's just keep that part. The rest of it looks nice. It's really hard to see, isn't it? Let's see, line width equals 2. Okay, that's pretty bold. But anyway, probably I wouldn't have that on a publication, a line that wide, but for the purpose of showing you the line in the video, that worked nicely. Okay, I put the line width down to 1. That looks pretty good. So notice how they're all centered and peaked at 0.2, the true value. They're roughly symmetric around there, and the symmetry increases as the sample size goes from 10 up to 100, and the variability also decreases as your sample size goes up. Okay. That was nice. I liked that demonstration. Do we answer all the questions? I don't think we answered any questions. Okay, how do the mean, standard deviation, and shape change? Okay, we talked about that briefly, so you can answer there. How do these values change if you increase the number of simulations? Okay, well, we could go up to 10,000 or 15,000 like they did before. You know, what you'll end up getting is just much smoother curves. Okay. If you went down from 5,000 to 50, these are going to be really chunky curves, right? Okay, those don't look like normal distributions at all. Okay. This is called Monte Carlo error. Monte Carlo has to do with randomness, like Monte Carlo, the city famous for gambling in Europe. And so as you increase the number of reps, the number of simulations, the variability due to sampling itself goes down because you've accounted for almost all the possibilities and in enough abundance that you're getting pretty good results. And even here you see this one had 5,000, 5,000 reps. But look at this distribution. It peaked not at 0.2 where it should have, but slightly to the left. There's some sampling variability there. And also this little step right here is a little steeper than it should be, and so this bar is a little too tall, right? As you increase the sample size, all those sort of defects of sampling variability go away. So here's now 25,000, and notice it's looking a lot smoother throughout. Okay, so anyway, it is important to have enough reps to get an accurate shape. How are we doing? Oh, we're at an hour, huh? Okay, so there's 4 more, I think, quick examples, and some of this I might just leave for you to do because I've probably given enough to answer each of these. Let's just make sure. Take a sample of size 15 from the population and calculate the proportion of people in the sample who think that this work scientists do enhances, so we've got a typo, enhances their lives. Okay, so just take a sample size 15. Okay, using the sample, what's your best point estimate of the population proportion? Well, if we didn't have any other information, if we didn't know what the true proportions in the population were, then the only evidence you would have would be of the sample from size 15. So that would be your best estimate. Why would, if you estimated something from the sample of 15, why would you think the estimate was anything different than what you observed? That's sort of the question. So I guess we can probably copy, right? We had this props from 50, so maybe just, but this has a whole bunch of reps. We just want one replicate. So here we go. We sampled. Oh yeah, so from one of our initial samples, right? We'll just copy this from sample 2, bring it down to here, and then you can set this to 15. Maybe call this sample 3. So if we block this and we replace sample 2 with, how about sample props? I don't really like that. How about 15? And we'll do replace. Oh, it went outside of my selection, so I got to be careful. That's why I didn't do all. I guess I didn't have within selection. I probably didn't have in selection highlighted, which I should have. Okay. Here we go. So blah, 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 blah. Okay, so there's what we observed. We've got the not benefit is 1 in 15, okay, 0.06. So in my sample just then, I got very unlucky. I'm miles away from 0.2. So But that is the best estimate based on the data for me right now. All right, exercise 8. Since you have access to the population, simulate the sampling distribution of proportion you think that it does enhance their lives of size 15 by taking 2,000 samples in size 15. Okay, this is very similar to what we just did. Plot the data and then describe the shape. Based on the sampling distribution, would you guess that the true proportion of those who think that it does enhance their lives, what do we think it would be? Finally, calculate and report the population proportion. Calculate, from the population data. Okay, well, we can do exactly that. It's just what we did up here when we did this small, basically. It seems a little bit redundant. So we've got size 15, reps 2,000, and sample size of 15, reps 2,000. It's not really important to change these labels, but if they're going to exist on the plot, they should be right. Okay, so maybe instead of props small, let's change that to props, come on, in selection, props 15. Did my next? Oh, that's dumb. Okay, so the selection went away. So I guess I've got to select. Oops, is this, where was I working? Exercise 8, sorry about this. This is not my main editor. I'm not this clumsy in my own work. Okay, so we're going to find the next one, replace. Okay, just 3 places. To replace it, blah, blah. Okay, so based on the sampling distribution, what would you guess the true proportion of those, okay, who benefit, right? So we want to do enhance. Okay, so that's the other option. So benefit, I think, is the label that we're looking for. Benefit. Is there anything else of interest here? I don't think so. So now we're looking at the proportion who benefit. What did I do wrong? Maybe the word benefit isn't right. Or benefits. I've already forgotten. Global monitor. Scientists work table. Benefits. Okay, that's why I didn't have the appropriate label. So when I went to count it or filter it, there were nothing with the word just benefit. So, all right, it's good to make errors. So you can see that. So let's try, say, 0.05 as a bin width. It's maybe slightly better. We do have these gaps. That's good enough. Okay, what were the questions now? What would you guess? So I would probably guess the center of this. Probably the mean, if I had to guess, the mean of the sampling distribution. So we've got p hat, and we can calculate the mean. Okay, that's my best guess right there. 0.797. And then finally calculate and report the population proportion. Well, our population is in the global monitor, and that's just calculating the proportion of the benefits group. So we can make a table. We've seen this before, and then from there we can do a prop table. So it calculates the proportions from this table. So there's my true proportion, 0.8. Excuse me. All right, thank you. All right, exercise 9. Change your sample size from 15 to 150. then compute the sampling distribution using the same method. All right, put it in this new object. Describe the shape of this sampling distribution and compare it to the one from 15. So this one you can see is slightly left skewed. Based on the sampling distribution, what would you guess the true population is? So I'll let you sort of do this yourself, or maybe I'll just do it very, very quickly without much commentary, because you've seen all of this before. So we're just going to change the dataset name to from 15 to 150. Here, let's give ourselves a little more space to see everything. Size 150. I think that's it. With a size of 150, we can go smaller in our bin width. Okay, our best estimate is 0.802, and that's what the distribution looks like. Now, why do we have some peaks that are high and some that are low? It's because our bin width is not really aligned with the resolution of our sample proportions. The sample proportions, p hat, if we look at the unique values and then we sort them, so here's 0.7, then it goes up 0.706 and 0.713 and then 0.72. So even though we have a bin width of 0.01, we have 3 values to fit in the space of 0.2. 3 doesn't fit into 2. So that means that 2 of these numbers will be grouped into one of the bars, the tall ones, and one of the numbers will be in a bar that is down low. So that's why we have that unusual situation. What we could do is we could set the bin width to be 1 over 150. Right? Then every observation should get its own bin. That looks better. Yeah, there are. I think that should probably always work. I'm thinking about the end conditions because there's like a 0 over 150 and 150 divided by 150. But even then, if the bin width is 1 over 150, yeah, every potential observation should get its own bin, especially because these bins are centered on each of the values. Anyway, there's some technical issues there, but okay, that's the nicest way to make nice bin widths in these scenarios of proportions. Did we answer all the questions based on this? Okay. Anyway, I think you can answer those questions. Exercise 10 is the last one. Of the sampling distributions from 8 and 9, okay, that's these exercises 8 and 9, I think that they made a typo over here. They say something like at the bottom here, of the sampling distributions from 2 and 3, which they're talking about exercises 8 and 9, which has the smaller spread. Okay, so we would sort of need to look at the axes of these two plots. Okay, so this is from a sample size of 15. The range here goes from 0.4 up to 1. For the sample size of 150, that I failed to label, I didn't change the label on the plot. The range goes from 0.7 up to 0.9. Okay, so this range is much narrower than this other range from 0.4 to 1. Okay, so what was the question? Which has the smaller spread? As you have a larger sample size, you have more information, so your uncertainty decreases. Smaller spread. If you're concerned with making estimates that are more often close to the true value, you would always prefer a smaller spread, which you get from a larger sample size. All right, so I've taken you all the way through, an hour, 10 minutes. Sorry going so long, but I hope that there was a lot of specific learning opportunities in this video for you. Let's render this, make sure that it gives us some output, and I didn't accidentally introduce an error that affects all of you. Okay. I often introduce errors, so you should go through and check. So let's make this a bit smaller, and I'll just sort of scroll down through and make sure that we've got plots that look okay. we've got some tables output. Also, the other thing to watch out for is sometimes you can output something that has tons of output and it goes on for like 20 pages of just a big string of numbers or something. We want to make sure that we don't have a big messy situation like that. You know, we got some weirdness there from samples of 150. That's because we only have 2,000 samples and we just had a bit of randomness here on the left. Actually, it's all randomness. Okay, the other place that, notice that this plot, relative to the other plots, maybe should be a little bit bigger. So let me just, you know, it is nice to fine tune some of these results. This is why I have the figure width and figure height options right here at the bottom of the YAML header, so that you can quickly copy that, go down to, let's see, I'm just going to look for facet, because I know that's, oh, in selection, uncheck that, next. Okay, so it's this code chunk here that has the facets at the top of here. That's the default sizes. Let's mostly make it taller probably. So figure height, because we've stacked these up, instead of 4, let's make it 8. So it's twice as tall. So I think it's helpful in, you know, these reports are not only communication, but specifically visual communication. And it's worth taking a little bit of time. I'm going to refresh the page. Okay. That's maybe a little bit too tall. Maybe 6 would be plenty. But you can see it sort of makes a difference, you know, to go and refine a few of these figure heights and widths occasionally to improve the presentation. Okay. I think that's a good place to wrap up. Thank you for sticking with me on this video. I hope, especially, you know, the main takeaways here are about, you know, something about completing incomplete rows, the idea of making a list and stacking a bunch of data sets and then binding them together and printing using the facet. You know, that is a really excellent skill when you're doing these types of comparisons. Yeah, otherwise it was just a bunch of sampling distribution stuff. So I hope you enjoyed that.